Assignment 25, 6.2, we're continuing, and today we're just going to talk about the graphing of polynomials and specifically the end behavior. We're not quite going to talk about how to find the zeros or the roots or the solutions yet, but I am going to show you how to graph polynomials just by looking at them and understanding what their end behavior is. So your essential question is, how do you determine end behavior of graphs of polynomial functions? And we've already done an exploration on this. We worked with Desmos, and hopefully you have a pretty good understanding of what's going on, and now I'm just going to summarize it for you. Okay, so end behavior. And we're going to break it up with a table. So we're going to have the leading coefficient in one column, we're going to have the degree in the next column, and then the last column will be the end behavior. Under degree, I'm going to put a little graph, so we want to give ourselves a little bit of room, a little bit extra room maybe. Okay, actually I should just go ahead and draw a nice solid line here for the headings of each column. And I'll try and get as close to my leading coefficient as possible because that's going to actually be the smallest column. And then as close to end behavior, we're going to write some stuff here, so we need a little bit of room. Okay, and I'm not sure how far down we'll go. All right, so leading coefficient. So you have a polynomial in standard form. So the polynomial has to be in standard form, okay? So maybe we should write something like, if a polynomial is in standard form, then we can say the following, then, okay? All right, so leading coefficient. So we're going to talk about whether that leading coefficient, which is usually, we usually use an a for that, right? And it's like in front of, for example, the x squared or the x cubed or the x to the fourth, okay? But if that leading coefficient or that a is positive, and the degree then is even, so as an example of that, I'll put an i.e. Y equals x squared. Now you're really familiar, hopefully, with this graph, right? It's just a parabola that's facing up and going through the origin. So I'm going to have a parabola facing up through the origin. So what we can say here is that as x gets big, right, as x increases to the right, so does y. And as x decreases or gets really small, y also grows, right? So now this is going to be kind of crazy notation for you, but just do your best, okay? So we can say that as x goes to infinity, so I'm just going to put as x goes to infinity, right? So as x gets really big, y also goes to infinity. You know what? I'm not going to use y. I'm going to use f of x. F of x goes to infinity. Okay? And vice versa, if we're looking at it at the negative x side, so as x gets really small or as x goes to negative infinity, then f of x is still getting big, right? It's still going to infinity. All that means is that it's basically up on both sides, right? It's getting, your outputs are getting positive on both sides. Okay, so that's whenever you have a positive coefficient with an even degree, such as a quadratic equation. And you guys are really familiar with this, right? Quadratic equation, when a is positive, it opens up. And that's all that this is saying. Okay, so what happens when your coefficient, your leading coefficient, a, is positive, but your degree is odd now. Okay, and we've worked with like y equals x to the first power. I'm going to introduce you to y equals x cubed. So let's see. So the graph of y equals x cubed is interesting. It's basically down on the left side and up on the right side, similar to y equals x, right? So when we had y equals x, we just had a straight line. Okay, so this one is, it's down on this side. Now it comes to the origin and it flattens out and it curves back around. So it goes from being concave down to concave up. Okay, so there's this point of inflection right here at the origin. And it is a flattened root. Okay, and maybe you explored this, or maybe you picked up on this. If not, I'll definitely go over this. But anywhere where you have a cube going through the origin, it's going to be flattened, or going through the x-axis. We call that a root, right? And it's a cubed root. So basically, it's a solution that's being cubed. So here, that's why it flattens out and goes through. Whereas this is a squared root, right? Okay, that 0 is being squared. Okay, and so that makes this where the graph will come down, touch the x-axis, and then double back. That's a double root, a triple root, or a cubed root. Okay, so there's a difference there, and we're going to talk more about that, so you don't need to take really big notes on that right now. All right, so let's talk about the end behavior then. Let's describe the end behavior. So on the right-hand side, let me label my axes. As x gets big, so does y. On the left side, as x gets small, y gets small. Okay, so we're going to have our end behavior description says that as x goes to infinity, then f of x also goes to infinity. Okay, and as on the other side now, as x gets really small, or as x goes to negative infinity, then f of x also goes to negative infinity. So it's important to be able to write this. Your book, the way that they'll write it is they'll put f of x first. For me, we always go x first, so I like to like when we're plotting points, right? We go x and then y, so I like to put it in this order. And you'll see when you check your answers, you'll be like, oh, wait a minute, it's backwards. It's fine. All right, so now we've only talked about positive coefficients. What happens when your coefficient is negative? And what happens when your coefficient is negative and you have an even? So for example, when we had like y equals negative x squared. Okay, well, you already know this one. What's going to happen to these end behaviors? They're both going to point down, right? This is a parabola that's facing down. Something like that. Probably not a very good parabola. And now let's describe the end behavior. So as x gets big, y gets small. As x gets small, y also gets small. So we can say that as x goes to infinity, f of x goes to negative infinity. And as x goes to negative infinity, right, going towards the left, then f of x also gets small, right, because y, your outputs are getting smaller. So negative infinity. And so we use infinity as a way of saying big or really small. Okay, infinity is not actually a number, it's a concept. You're just saying as x gets really big. Okay? And one more of these, because we don't have when your leading coefficient is negative and your degree is odd, so we still need to take care of that. Okay, so leading coefficient negative, your degree is odd. So for example now, I'm going to use y equals negative x cubed. But think about a line. So if this was y equals negative x to the first power, a line with a negative slope basically goes from left to right. It's going down, right? And our last cubic that we had, which was positive a, or positive leading coefficient, it was just like a line, right? Where it went from being down to up. Okay, so the same thing's going to be true now when we have it negative coefficient, leading coefficient. We're now going to start up here, come through the origin, and go down. Okay, so that's what that graph's going to look like. This one's a little bit more tricky to draw, but again, remember it flattens out at the origin. That's that cubed root or that triple root, and comes down. Okay, so we can say then that as x gets big, y gets small, and as x gets small, y gets big, right? So as x goes to infinity, f of x goes to negative infinity. And then the other way, as x gets small, or as x goes to negative infinity, y is getting big. Or going to infinity. So when you're thinking about, let me zoom out here. So when you're thinking about these polynomials, this is it. This is your guide. When you're thinking about graphing these things, if the leading coefficient is positive, even or odd, you know what the end behavior is going to look like. If the leading coefficient is negative, even or odd, you know what the end behavior is going to look like. Okay, so what I want you to do when you're doing these is I always want you to think of everything polynomials in terms of quadratics, which is the x squared, or cubics, which is that x cubed. Okay, so you have a good guide. Now, all the stuff in between will change. Okay, there may be lots of humps in there, lots of extrema, right? But the end behavior is what we really are concerned about in this lesson. So moving on, let's do some examples. All right, so example 1. Describe the end behavior of the graph. Oops. So that's basically this description right here. This is the end behavior description, is this last column. Okay? So the first one, f of x equals negative 5x to the fourth. So I've got a negative leading coefficient and an even power. So let's see what that looks like. That's a negative coefficient, leading coefficient, even power. That's going to be just like your parabola facing down. Okay? The difference is this could have some humps. If it's x to the fourth, it could have more extrema. Okay? It could have, anywhere up to 4 roots. 3 extrema. 2 points of inflection. Okay? That's just like our exploration was talking about yesterday. All right, so thinking about that, I know that it's going to basically be going down on the left, down on the right. So now I'm going to describe it. And so my description comes directly from right here, right? So as x gets big, y gets small. And as x gets small, so does y. Okay, and I like to draw little pictures here to kind of just remind myself of what is happening. So as x goes to, and if it helps, maybe I could Draw an x and y axis. Maybe that helps a little bit more. So as x gets big, then we know that f of x goes to negative infinity. And as x goes to negative infinity, f of x also goes to negative infinity, right? It's going down. All right, let's try another one. How about f of x equals, we'll make this one a little bit more challenging, negative 3, oops, that's not what it is. X to the 5th, sorry, minus 4x squared plus 3. Okay, so we have a negative leading coefficient and an odd power, or an odd degree. So, negative leading coefficient, odd degree. The end behavior is going to be up on the left, down on the right. So again, I would probably draw myself a little picture. Up on the left, down on the right. It'll probably have a couple humps in there. Okay, maybe a few. Could have up to 5 roots. Some of them could be double roots. Okay, so we're not going to do all that right now. Don't worry, we'll get to it. You're really going to be able to like bisect these polynomials apart and figure out everything about them, but not just yet. Okay, right now all I'm doing is describing end behavior. So I know that as x gets big, y gets small. As x gets small, y gets big. Okay, so as x goes to infinity, f of x goes to negative infinity. And as x goes to negative infinity, f of x goes to positive infinity. Okay, maybe I should label my axes. Okay, so let's actually graph one of these to the best of our ability. Okay? So right now, example 2, we are going to graph. So first one, f of x equals x to the 5th plus 2. Okay, so the first thing you always want to do is you want to figure out the end behavior. Okay, so there's 2 steps here. 1, determine end behavior. And 2, XY chart. To get some more points. I would always include, for example, your y-intercept. Okay, so I'll maybe make a note here. Include y-intercept. Okay, that's going to be important. Just because it's something that you can actually get accurately. While right now you don't know how to find the zeros yet. So this is going to be the most that you can do. Okay, and then you can always check these on your graphing calculator. Don't just start by going to your graphing calculator, okay? Start by making a good guess of what these things look like, and then go to your graphing calculator. Okay, so the first thing I'm going to do is determine my end behavior. So I see that I have a positive leading coefficient with a power of 5, which is odd. So, positive leading coefficient, odd. I know it's going to be down on one side, or down on the left, up on the right. So again, the first thing that I do is I always say, okay, I know it's going to look like this. Okay, and then I start graphing it. Okay, so 1, I determined the end behavior. I'll put a little 1 there. And 2, I'm going to make an XY chart. Oops, the Y chart would go here. And I'm going to start with 0, right? I'm starting with that y-intercept. Okay, so I start with 0. So I plug 0 in here and I get 2. Okay, and I should definitely plug some things in around it. So maybe I'll do, how about -1 and +1? So when I plug -1 in, it looks like I get, that's going to give me -1, right? Because any negative to an odd power is still going to be negative. Add 2, I'm going to get positive 1. And then if I plug 1 in here, I'm going to get 1 plus 2 is 3. So make these numbers easy on yourself. Don't get too crazy. All right, so when x is negative 1, I'm about here. And when x is positive 1, I'm at 3. So about here. Okay, so this thing is actually, hopefully you're recognizing that this constant is what kind of shifts the center of this graph, right? So what would normally we call a vertex, not quite a vertex, but here it's actually going to be that point of inflection where this graph is changing. Okay, so this is what's going to shift the graph up 2, right? So originally you could think of this as like an x cubed graph, and then it was shifted up 2, okay? So I'm going to draw this to the best of my ability. It's gonna kind of flatten out and go back up. Okay, it's missing all of its other pieces. So like x to the 4th, x to the 3rd, x squared. Those would all give it more humps. Okay, it would give it more roots. Okay, this isn't going to have a whole bunch of real roots. It has some imaginary ones. Okay, awesome. So that was one graph. Let's do another one. Okay, we're going to do f of x equals x cubed minus 3x minus 1. Okay, so this graph I know has a positive leading coefficient and an odd degree. Okay, so that means that my end behavior is going to be down on the left, up on the right. Okay, and so you really need to get that through your head. Okay, so you need to think about these things in terms of everything that's on this table. Okay, so you're responsible for this. And if thinking in terms of x cubed is too challenging for you, you can always think of this in terms of a line, right? This is a line, y equals x. Or make this one a line, y equals negative x. Okay, if the x cubes are getting to you. But okay, so I know my end behavior. Now it's time for an xy chart. So I'm always going to start with my y-intercept. I like to do that, okay? If I plug 0 in here, this becomes 0, that becomes 0, so I get negative 1. Okay, now I'll plug in, how about a negative 1 and a 1? Okay, so maybe I should do a little bit of this with you. So when I plug in, for example, negative 1, f of negative 1, well, that is negative 1 cubed minus 3 times negative 1 minus 1. So negative 1 cubed is still just negative 1. This becomes a positive, positive 3 minus 1. So really you have 3 minus 2. So that's going to equal 1. Okay, and plug in a positive 1. That's pretty easy. So that's 1 minus 3 minus 1. So 1 minus 3 is negative 2. Minus 1 is going to be negative 3. Okay, let's see if I'm getting any information on this graph. This one might be one where you need to do a little bit more. All right, so 0, negative 1, which makes sense, right? This thing's been shifted down. Okay, negative 1 is up to 1. Something's wrong there. I'm noticing that my end behavior is supposed to go down on the left and up on the right. It looks to me like it's going to end up going up on the left. So I'm thinking, oh my gosh, maybe I'm making a mistake. But let's remember, there are humps in this thing. Okay, there's more extrema than we think. So I need to go further. Okay, so I might want to plug in, I don't know, let's see what negative 2 does for me. All right, so if I plug negative 2 in here, this is going to give me negative 8. Oh, my dog is getting in her toy basket. Negative 8 minus, let's see, plus 24. Nope, plus 6. Not concentrating because of the dog. She's running around like crazy right now. So let me go back to that. Negative 8, positive 6, minus 1. Okay, so this is going to give me a negative 2, a negative 3. Okay, so I'm actually going to be at down here. It's coming back around. Okay, now let's see what happens on the other side. Okay, so at positive 1, oh, I'm back down to negative 3. And I'm going to go ahead and plug in 2 just to make it somewhat symmetrical here. Not exactly symmetrical, but just so that I have the same amount of inputs and outputs. All right, so when I plug 2 in here, I get 8 minus 6 minus 1. So really it's 8 minus 7. Or sorry, yeah, minus 7, so I'm going to have 1. So that's 2, 1. Okay, so the way that this is going to work is it's going to be down on this side, head up, come back down and around. And I cannot guarantee right now that these are in fact the extremes. Okay, graphing this on a graphing calculator would probably tell you whether or not it's the extremes. Right now, you're not responsible for that. You will be in the future. Okay, when we can actually figure out what our roots are, you will be. Notice, though, how many roots does this have? It's x cubed, and it can have, at most, 3 roots. And this one does have 3 roots. So just for fun, I thought I would go ahead and plug this into our graphing calculator and see how close we came. Okay. Not bad, not bad. And if I changed my window, maybe so it's a little bit more symmetric. So let's see, we'll make everything. How about if I do a zoom and I can do a Z standard to make it a standard window, which means positive 10, negative 10. So you can see, okay, I didn't do so bad. Yeah, that's pretty much accurate. I mean, my graph could have been a little bit better, but all right, there it is. Check these things on your graphing calculators. Get good experience with your graphing calculators, and hopefully you guys would know at this point how to find these roots if you needed to.